In this session, we shall discuss the preparation of standard oxalic acid solution. Oxalic acid is a dibasic acid. Formula I have already known. That means you can simply write it like this: H2C2O4. Another formula form this also like this is the bonding form, and it contains 2 water of stabilization. So this is dihydrate. You can call it oxalic acid dihydrate in the thermal solution. And in this case, we have to prepare a standard solution. Standard solution means of known strength. A standard solution you have to use such reagent which will be stable, pure, which will not decompose, and which have high molecular mass. High molecular mass means there will be that weight can be much accurate one. But if you take 0.001 and then you take 1 gram, there will be discrepancy in taking 0.001, but you can get a correct weight in 1 gram. So for that reason, your standard substance that will be a standard solution of which the reagent is required, that should have high molecular mass, and that should be very stable. It will not decompose. Like suppose you take sodium carbonate and you take ammonium carbonate. This sodium carbonate is very much stable, but the ammonium carbonate, even by pressing it, there will be liberation of ammonia. For that reason, ammonium carbonate is called a smelling salt. Remember, ammonium carbonate is called smelling salt. If you are suffering from cold, you take ammonium carbonate in a handkerchief and rub it and smell it. So that will be sufficient to eradicate your fever from you or cold from you. So that is the smelling salt. So that will decompose. So ammonium carbonate cannot be taken as a standard solution or primary standard. So standard solution you can divide into primary standard and secondary standard. Secondary standard is that which can be standardized. Standardized means which the normality or molarity can be found out. The concentration or strength can be found out by titrating against a standard solution of which the normality is known or molarity is known. So standard solution was the solution of known strength that is known, and you have to titrate against the other solution of which that is not a standard solution or that not a primary standard. That secondary standard can be titrated or can be the concentration or normality of the solution can be found out by titrating against a standard solution. So here we need 2 things. One is primary standard of which the normality does not change if the solution is kept for years together. आज जदि आम सोडियम कार्बोनेट सॉल्यूशन कर दे जाइबा 5 दिन बा 7 दिन बा मासे 2 मास परे आसले सेटा सॉल्यूशन रो कोनसी कंसंट्रेशन रो परिवर्तन घटिबनी बा नॉर्मलिटी चेंज होबनी सही प्रकार सॉल्यूशन को वी कैन यूज एज ए स्टैंडर्ड सॉल्यूशन. बट इफ यू कीप प्रिपेयर पोटेशियम परमंगनेट for this year, after 1 year that will decompose, there will be deposition of manganese dioxide. पोटेशियम परमंगनेट जदि हम सॉल्यूशन कर जाइबा धर मासे 2 मास पर आसी हमें जदि टाइट्रेशन करिबा देखबा त नॉर्मलिटी कमी जाइछि because that is not a primary standard. So oxalic acid with water even that will be reduced. Potassium permanganate will reduce. So potassium permanganate cannot be used as a primary standard. So potassium permanganate strength or normality or molarity you can calculate by titrating against oxalic acid. So oxalic acid is the primary standard which can be used to find out the normality or molarity or any strength. Strength means grams per liter for a solution that is like your potassium permanganate. And we will be doing this titration in the coming year, and that is called a redox titration. Here in the redox titration we will be getting one reducing agent, another oxidizing agent, and their oxidizing agent will be potassium permanganate, reducing agent is your oxalic acid. And in that context also you have to prepare standard solution of oxalic acid. And I will show you that how the standard solution of oxalic acid m by 20, say 100 milliliter, let us filter only 100 milliliter can be filtered. So that means initially how much weight of oxalic acid needed. How can you calculate the weight of oxalic acid? In the m by 20, it is same as you know 1 mole of oxalic acid is equal to its molar mass, and the molar mass will be perhaps 126 H2C2O4 2 water. This will be 2 plus 24 plus 64. 64 this is equal to 90 and this is equal to 36. So that will be 126. 126 is its molar mass. That can be also expressed gram per mole. 1 mole if you take, the weight of that oxalic acid will be 126 gram. So its equivalent mass as it is a dibasic acid, equivalent mass if you take, it is a acid base titration, it is a dibasic basicity is equal to 2 because 2 replaceable H plus is there. So its equivalent mass is 126 by 2 is equal to 63. 126 by 2 it is equivalent mass. Even suppose in the potassium permanganate titration, that is also it can be used as a reducing agent. So reducing agent also, oxalic acid is not only an acid but also a reducing agent. Reducing agent. Why it is a reducing agent? Because oxalic acid oxidizes to oxidizes because it is a reducing agent. Reducing agent reduces others, but itself get oxidized. When oxalic acid oxidizes, you getting carbon dioxide and water. So here you find out the equivalent mass. Here one method is the number of electrons involved, or another method is to what mass it will be equivalent to 8 gram of oxygen. 8 gram of oxygen means oxygen 1 gram equivalent. Oxygen atomic mass is 16, valence is 2, so 16 by 2 is 8. So 8 gram of oxygen, jette gram of oxalic acid saହିତ मिसिबो सेटा आज तार equivalent mass. So here 16 gram is 1 mole saହିତ, to 8 gram is half mole. So in that case also multiplied by 2, in this case also multiplied by 2. So whether oxalic acid is behaving as an acid, the equivalent mass is also half molar mass, and if it is acted as a reducing agent, where in case of potassium permanganate, that also is molar mass by 2. Also you can calculate, as I told you, so in oxalic acid is equal to 2 carbon dioxide plus 2 electron. As number of moles of electron is 2, so molar mass by 2 is equal to its equivalent mass. So equivalent mass equal to molar mass divided by number of electrons involved. Involved means it may be added or subtracted. If it is subtracted, that means that is a case of oxidation. If it is added, that is a case of reduction. So whatever the case may be, number of electrons involved will be divided to its molar mass, so that you can find out the equivalent mass. So this is 63 is its equivalent mass. Then suppose in this 1 mole, that means in this case what you find, 1 mole of oxalic acid is equal to 2 gram equivalent, because molar mass is 126, equivalent mass is equal to 63. So 1 mole is equal to 2 gram equivalent. Or if you take 1 ml solution, this will be equal to 2 normal solution. That means 2 gram equivalent per liter, 1 molar solution means 1 mole per liter. So if you put it here 2n by 2, that means it is n by 10. So n by 10 or decinormal solution is same as your molar solution. Molar solution if you express, that will be m by 20. So m by 20 is same as n by 10 solution. So n by 10 because 1 mole is equal to 2 gram equivalent. So you have to prepare, say, let us say n by 10 solution of oxalic acid. So 63 gram in 1 liter gives 1 normal solution because this is the equivalent weight. 1 gram equivalent, that is equal to 126 by 2. 126 by 2. So 63 grams in 1 liter gives 1 normal solution. We have to prepare decinormal solution. So n by 10 is equal to, it will be of 6.3 gram. N by 10, this is your per liter, 1 liter. And if you prepare 100 milliliter, 1 liter needs 6.3 gram. So 100 milliliter will be 1/10 of that. That will be 0.63. That means in 100 milliliter solution, we have to take 0.63 gram so that we can have a decinormal solution of 100 milliliter. So let us prepare a decinormal solution of your oxalic acid, dihydrated oxalic acid. That means you have to take correctly, weigh out points because this is a standard solution. Your weight must be correct, volume must be correct. Two things must be correct. Your weight must be correct and volume must be correct. So volume will be 100 milliliter. This is a 100 milliliter measuring flask or volumetric flask, and in this you have to weigh out 0.63 gram of oxalic acid. We shall show you how to take weight and how can you prepare this solution. So this is your electronic balance, that will be easier, and to take the weight, this is a solid crystalline substance. Take the weight, you have to take the watch glass, or even in a paper, that is the paper means blotting paper or tissue paper or your filter paper. It will be better to take the weight in a filter paper. And if you take the weighing bottle or this watch glass, you have to take the weight of the watch glass. So, or with the watch glass you can manage also up to 0 also you can manage. Or if you not manage at 0, then you take the weight of the watch glass and you put the substance, and by the difference of weight you can find out the weight of the substance. And here you have to add such that will be coming your 0.63 gram. Let us take 0.63 gram of oxalic acid dihydrate. Remember that weight must be correctly taken. Your standard solution must have definite quantity of weight in a definite volume of solution. Gram equivalent per liter of solution. Similarly, gram equivalent in the from liter of in this case 100 milliliter solution. So this is your 0.63 gram of oxalic acid. Let us how to transfer it. That is also important. How to transfer it to the measuring flask. You take a funnel, wide mouth funnel, then quantitatively, remember quantitatively that to be transferred. Not a single or molecule will be taken outside or split outside. So very cautiously you have to transfer whole quantity of the oxalic acid to the measuring flask. If a little variation is there, there will be variation of normality or molarity. That means here apparatus used is your balance, then your funnel, then your watch glass, then your measuring flask, and a wash bottle. To make the volume up to the mark, that means if a mark is there in your measuring flask, and it is a colorless solution, it should be added to water. So that lower meniscus of water will be just touching the like. At this point, suppose you fill up to this, from this to this, you can take use of, if you are no so pasas, so experienced, you can take the help of a pipette. Taking the pipette, you add water dropwise so that this water level will touch lower meniscus of the water level will touch the your mouth. In that condition, a measuring process. You can also take this wash bottle for making the volume also.
Mark is here. So we have
You see the mark.
mark is here, so we have to make the volume up to the mark so that it will prepare a solution for FY. Now the volume is up to the mark. You can shake the solution to have a uniform solution.
In connection with the oxalic acid, now we have standard solution is prepared. Now we have to standardize sodium hydroxide. Sodium hydroxide cannot be standardized against hydrochloric acid. Because hydrochloric acid is not a primary standard, so also sodium hydroxide is not a primary standard. Question is asked in the Viva, why sodium hydroxide is not taken as a primary standard, but sodium carbonate is taken as a primary standard. Sodium carbonate does not decompose on weighing its weight, never changing. Understand? Now, sodium carbonate is a primary standard because it is a stable compound available in pure state. But sodium hydroxide for in the market it is available in pellets, and that pellet is very hygroscopic also, and on exposure sodium hydroxide may convert into sodium carbonate. We cannot accurately measure sodium hydroxide because during the process of weighing the weight gets increased due to absorption of water and carbon dioxide. So sodium hydroxide subsequently after some days it will be converted into sodium carbonate. The sodium hydroxide, the upper layer may also contain some portion of sodium carbonate. So as it is not a stable compound, this is hygroscopic and converted to and combined with the other compounds, so it is not taken as a primary standard. So sodium hydroxide cannot be titrated against hydrochloric acid. So here we can titrate against oxalic acid because we have prepared the standard oxalic acid now sometime before. Understand? So sodium oxalate or oxalic acid also is a primary standard, and with reference to oxalic acid we are preparing decinormal solution of decinormal or n/20 solution of oxalic acid, and with reference to that oxalic acid versus sodium hydroxide. So this is not a primary standard. This is not a primary standard. Approximately you take the weight of this, because say prepare some sodium hydroxide has molecular mass 40 and its equivalent mass is also 40. Why sodium hydroxide has identical equivalent mass and molecular mass? Because its acidity is 1. Acidity means the number of H plus ion that it can necessary for neutralization. Sodium hydroxide plus hydrochloric acid. It gives 1 mole of OH minus and 1 mole of H plus, say, hydrochloric acid. So sodium hydroxide is neutralized by 1 mole per mole of sodium hydroxide. So this is a monoacidic base. sodium hydroxide is called monoacidic base. So its acidity is equal to 1. So molecular mass by acidity is equal to its equivalent mass. So its molecular mass is 1, acidity is 1. So its molecular mass is equal to equivalent mass. So it's 40 gram, you can call it 1 gram equivalent. Also you can call it 1 mole. Also you can call it 1 mole. So that 40 gram 1 mole present in 1 liter, that you can call it 1 molar solution, and also you can call it 1 normal solution. Their normality is equal to molarity because equivalent mass is equal to molar mass. So 40 gram in 1 liter, that means a normal solution. If you 1/10 of that 1/10 of this, that will give you test normal solution or n by 10 solution. So if you need 1 liter of n by 10 sodium hydroxide, you have to take 4 grams. So it is not necessary to take 1 liter of this. Let us prepare a minor quantity, say 100 milliliter, very less quantity of sodium hydroxide. We should be very cautious of utilizing these chemicals because these are very costly chemicals. So we must be minimum in utilizing it. So 4 gram in 1 liter, that will be n by 10 solution. But instead of preparing 1 liter, we are 1/10 of that. So we are preparing 100 milliliter of n by 10 solution. 100 milliliter of n by 10. So in this case, that means 1/10 of this, for 1/10, that means 0.4. So you have to take 0.4 gram of sodium hydroxide, few pellets of it, and dissolve it slowly with the sodium hydroxide. Then as it is, we are preparing oxalic acid, similar way you prepare n by 10 sodium hydroxide. So that sodium hydroxide is already, we have already prepared. So in that case, there is a weak acid versus a strong base titration. So here, instead of methyl lorraine indicator used for strong acid, strong base, but this is a weak acid, strong base. For this, phenolphthalein indicator is used. This phenolphthalein indicator we have now it is in the prepared form also available in the market. If you are so much economical, you packets of phenolphthalein, you bring it, and that packets you dissolve in alcohol and then dilute it to water. That will be a phenolphthalein solution. But we have a standard solution as marketed by some company. So that phenolphthalein, you remember why that is an indicator. Phenolphthalein is an indicator because the color change can be appropriately marked because its acidic color is colorless and alkaline color is pink. So by this change in color, because we are going to take the acid, this type acid, the titrate, because it is known normally it is there. As the strength is known, you can make it in the burette, acid is taken in the burette, and alkali is taken in the burette. So prepare, you take 10 milliliter of the prepared out sodium hydroxide, to which you put a simple drop of phenolphthalein, and phenolphthalein, the alkaline color is pink, totally the solution turns into pink. Then add on dropping out or adding the solution of oxalic acid from the titrant that is in the kept in the burette. Slowly when the color getting faded. If at some time the color persists for a color fades completely, or complete fading of color indicates the approach of the end. Simply or equivalency point. So in this case, your titration, by change of the color, that is from pink to colorless, when the pink color just discharges, that will give you the end point. So by this, let us show you the experiment regarding how the color change occurs.
Now, the oxalic acid is already been prepared, and we are going to do the titration with the help of the burette, the pipette, the polymer flask, and the burette stand. So first of all, as you know, this is a burette. It is a long cylindrical glass tube. One end is open and the other end is just fitted within stopper. So you have to hold the burette in such a way that the markings you can see on your screen. So first, we just take some amount of oxalic acid and just close the other end with the thumb and rotate it or rinse it so that all the waste cycling of the fluid get crossed with the solution. So this we are doing rinsing. As we have washed the burette with water, some amount of water may be taken to the walls of the burette, and if you directly take the solution, then it may get diluted. If it is a dry one, you can take the solution without rinsing. So now I am filling it with the standard oxalic acid, whichever we have prepared. Now while filling the burette, make sure that the knob is closed. So if the knob is open, then you can use the solution to be drained. Now while filling on the burette, just take the burette or take oxalic acid above 0. This is the 0 mark, and we have to take it above 0 because we have to maintain the air gap below the knob. So now just I am maintaining the air gap. Then we have to check the meniscus to get the correct or the exact readings. Now you open it slowly so that you can adjust it to 0. Once you do it, just check it with your eye level. Yes, it is 0. Now we have to fix the burette and set up for the titration. Now you know this is a burette stand. We have to fix the burette, the knob towards the right hand and placing the conical flaps below it. It should not be inside the conical flaps, or else it will have problems in taking out, and neither it should be too high so that the solution cannot get into your conical flaps. Now in this, the top tip of the burette and the conical flaps should be closer to each other, and you fix it. Just tighten so that the burette gets fixed, and make sure before leaving your hand that the burette is fixed. Now conical flaps also we have to push it with one hand. Now for pipetting, already this NaOH solution is there. So this is your NaOH solution standardized. This is the pipette. And the most important aspect of pipetting is how to hold the pipette correctly. So pipette, the most important thing that we have to hold it with these 2 fingers, and this index finger should be released so that you can adjust it. So for rinsing, I have to take some amount of solution. Then again the same way you roll it like a burette and drain it. If it is a dry one, you can directly take the solution. Now for pipetting, you have to suck it. So after this, like now you have to adjust with drop twice. Now you see it is 0. When it is 0, you have to press it. No more solution will be coming from the pipette. Now it is 10 ml. Then you transfer this 10 ml NaOH solution to the conical flaps. After the solution is drained out, just see some amount of solution is taken to the tip of the pipette. So what you do, you slant the conical flaps and touch the tip of the pipette twice or thrice so that the total solution in the pipette is drained out in the conical flaps. Now you have to place the conical flask below the burette and add oxalic, we have to add this phenolphthalein indicator so that just see what happens when we add the indicator solution. We have to take 1 drop of indicator solution. You see the color is completely dark pink. So as you all know, phenolphthalein gives pink color in basic medium and in acidic medium phenolphthalein becomes colorless. So as we are going to add oxalic acid from the burette, gradually this pink color will start disappearing. Now you see, this is the way how you have to handle the burette. So just adjust the burette knob dropwise and go on shaking the conical flask till the pink color becomes colorless. Be careful while shaking, or else you may break up in, or else it will be end up in breaking. This is the way how you have to do the titration.
With the phenolphthalein, the color is dark pink, and now it gets colorless. Let me see the final burette reading. This is 5.8, 9.8. The final burette reading is 9.8, and the initial burette reading was 0.0. So 9.8. We have taken 10 milliliter of sodium hydroxide. This is 0.2. Final burette reading is 9.8. So the difference is 9.8 milliliter. Difference is 9.8 milliliter. So in this, I am not repeating the second and third and fourth readings. You yourself, when you calculate this, yourself do it, and you see that if it comes 9.8, 9.8, suppose one comes 9.9, don't erase that reading. You keep it here. Then you go for the third reading and fourth reading. Fourth reading comes 9.8. So the concordant value 3. Suppose if we are now getting 4 readings. Out of this 4 reading, the first reading, second reading, and fourth reading are concordant one. So concordant value in milliliter, it will be 9.8. So for calculation purposes, we have to choose 9.8. Don't take 9.9. If 9.9 will be repeatedly coming thrice 9.9, then you can take it. So if any other mistake is carried out, so that the difference reading is found, you don't erase that or don't cut out that. Don't cut out the table or don't repeat the table. That will have a negative impression on you. So if by any mistake it comes to be 9.9, then you keep it in the table and go for the other reading till it comes 9.8. So if there will be 3 readings concordant, that value will be taken for calculation. Then let me calculate on the basis of this tabulation and on the basis of the normality of the oxalic acid. So oxalic acid normality is n by 10. On this basis, let me calculate the strength of or normality of your sodium hydroxide. Because sodium hydroxide is not a primary standard. Now we go for calculation. That means in this process we have gone across so many steps. First step, you are getting into preparation of different solution, including the phenolphthalein indicator. If it is not available, you have to make a solution of phenolphthalein indicator by dissolving in ethyl alcohol and diluting in water. So all these things you have to prepare yourself. Of course, in the examination you will be supplied with the solution, but in the laboratory you have to prepare all these solutions. Specifically, you must have to prepare oxalic acid because that is the standard solution. You have to have on you, you may not believe on the others preparation. So you have to sure have the preparation of standard oxalic solution, which is calculated to be n by 10. Then on this basis calculation, how the law of equivalent or equivalency comes into play in chemistry. Very interesting observation is finding. Suppose sodium hydroxide. So that on the basis of this is a caustic soda, this titration is called caustic titration. This is acid base titration no doubt, but if that oxalic acid is titrated against potassium permanganate, that is called redox titration. Different types of volumetric analysis are there. So this is called acid base titration, or as sodium hydroxide is used. Sodium hydroxide is known as caustic soda, so it is named as caustic titration. So sodium hydroxide plus oxalic acid H2C2O4, you will get sodium oxalate salt plus water, 2 water. It is balanced 2 water, sodium hydroxide, 2 sodium hydroxide. So you see, from this how can you the equivalency law you can find out. In a chemistry we have get a very good observation. Also that observation will apply in stoichiometry calculation. Law of stoichiometry. For stoichiometry calculation, we will mostly apply that for our easier way of understanding. So here you see, if you consider mole, this will be moles of what? Alkali. This is moles of acid. That molar ratio is 2:1. Molar ratio is 2:1. Molar ratio is 2, that means M1 V1 by M2 V2 is equal to 2:1. If the molarity form. But if you do how it comes to the normality, you find out. 2 moles of this equation, this balance equation, told us 2 moles of alkali or sodium hydroxide is equivalent to 1 mole of acid or oxalic acid. This is the molar. Molar is not 1:1, but equivalent will be always 1:1. Suppose A plus 5B gives out 10C. So in that case, 1 gram equivalent of A will react with 1 gram equivalent of B to give you 1 gram equivalent of C. This is a very interesting observation in chemistry. All will come in gram equivalents. Suppose A plus NB is equal to C. That is 1 gram equivalent of A reacts with 1 gram equivalent B to give you 1 gram equivalent of C. But the molar ratio is not 1:1. The molar ratio is 1:9 and 1:20. 1 mole of A combined with N moles of B. So molar ratio may differ, but equivalent ratio will be always 1:1. So for that reason, the molar ratio is equal to the stoichiometric coefficient. And here stoichiometric coefficient is 2 and 1. The ratio will be 2. Gram equivalents of alkali by gram equivalent of acid in gram mole of acid is equal to 2:1. That is by that also you can calculate the molar form, molarity of other, but it is easier to calculate in normal form. So how it becomes normal form? 1:1, 2 moles of sodium hydroxide, you divide it by 2, this is also divided by 2. This is not wrong in expression. That means 1 mole of sodium hydroxide will react with half mole of oxalic acid. Now you see, sodium hydroxide is a monoacidic base. That is a monoacidic base. So this is the as basicity is 1, its molar mass is equal to equivalent mass. So 1 mole of sodium hydroxide, you can very well write 1 gram equivalent of sodium hydroxide. 1 gram equivalent of sodium hydroxide. And half mole of oxalic acid, as oxalic acid equivalent mass is molar mass by 2, because this is a dibasic acid. So in that case, it is half mole is the same as 1 gram equivalent of oxalic acid. This is very interesting observation. Gram equivalent of acid will be equal to, or will be not equal, you can call it equivalent. Equivalent to, parallel to each other. Equivalent is a sign of equivalency. Equivalent to 1 gram equivalent of alkali must be equivalent to 1 gram equivalent of acid. Similarly, 1 gram equivalent of reducing agent must be equivalent to 1 gram equivalent of reducing agent. So equivalent weight of oxidizing agent and equivalent weight of reducing agent are also in the ratio of 1:1 by gram equivalence. You remember, this is the law of equivalency. Suppose 1 gram equivalent of one will be equivalent to 1 gram equivalent of other. The molar ratio in some cases that will may be equal, but not always. As for example, sodium hydroxide plus hydrochloric acid. It is the molar ratio is the same as the normal ratio. So 1 gram equivalent of sodium hydroxide is equivalent to 1 gram equivalent of hydrochloric acid because sodium hydroxide equivalent mass is the molar mass by 1, hydrochloric acid equivalent mass is the same as also its molar mass. So in this case, there will be no difference. That means here molar is also 1:1. 1 mole of this is equivalent to 1 mole of this. And also in the equivalent, 1 gram equivalent this is equivalent to 1 gram equivalent of that. That means acid and base reacting the ratio of 1:1 by gram equivalent, also 1:1 by gram mole. So this is the interesting way. So let me calculate 1 gram equivalent is that is present in 1 liter, that is 1 normal solution. So for that V1 and 1 it comes to like this. The number of gram equivalent, you know, the normality is equal to W by E, that is the number of gram equivalent. Mass of the substance divided by equivalent mass is equal to number of equivalents. So number of equivalents is equal to W by E. If it is molecular mass, it is called number of gram mole. So this is called number of gram equivalent. And I am telling number of gram equivalent of one is equal to number of gram equivalent of other, and W by E into 1000 by V. If it is 1 liter, V liter, you have to consider 1 by V. But if you consider it in milliliter, then liter is converted to milliliter. So you see in this case, W by E is equal to N by V, N into V. W by E is equal to N into V by 1000. Or N into V, you can call it milliequivalence. Equivalence, 1 by 1000 of it is called milliequivalence. 1 equivalent is equal to 1000 milliequivalence. And 1 milliequivalent equal to 1 by 1000 gram equivalence. So you see, this is the N by V is equal to the gram equivalent. So you put it here, you put it for say alkali, say 1, as oxalic acid, say 2. So normality into N1 into V1. N1 means normality of sodium hydroxide, V1 means volume of sodium hydroxide. So N1 V1 by 1000 is equal to N2 V2 by 1000. That means gram equivalent of sodium hydroxide is equal to gram equivalent of oxalic acid. And that means we can replace this by cutting 1000, 1000. So you see N1 V1 is equal to N2. Or milliequivalence of 1 is equal to milliequivalence of 1. So this is a very interesting observation during our titration process. That means gram equivalent of 1 is equal to gram equivalent of 1. So students, you can remember, you can put this such type of stoichiometric problem in the form of gram equivalence or milliequivalence. You can calculate through milliequivalence also. But don't go through by balancing equation and find out the molar ratio. That will take time. But if you take the equivalent form, the calculation will be easier. So, you see, normality of, say, this is for alkali, this is say for acid, and here acid is oxalic acid. So, alkali normality we have to calculate. Alkali normality to calculate because that is not a standard solution. We cannot prepare exactly n by 10 or 1.0 to n by 10 of sodium hydroxide. Normality is N1. V1 is the volume of alkali. N2 is the volume of the normality of oxalic acid. V2 is the volume of oxalic acid. So normality of, you have to calculate the normality. Calculation of normality. This is for alkali. Volume of alkali we have taken 10 milliliter. That is correct. We have taken the pipette 10 milliliter, and that is N2. N2 is n by 10. N2 is equal to n by 10. That is normality we have prepared, or any something into n by 10. If you exactly not take the say 0.63 gram, if anything in that case, that you also can calculate the normality in some factor will be there. Suppose 1.02 n by 10. But here we have prepared in the decimal form or m by 20 form. So this is the n by 10, and V2 is the volume of oxalic acid, that is the titrant value 9.8. The Biret reading, the difference in Biret reading. So this is the case, so that only unknown factor is the N1, that is the normality of alkali. So normality of alkali is equal to 9.8 by 10 m by 10. Because you see, if one is given in the n by 10 form or decimal form, your answer should be in the decimal form. But in case of benz acid in the coming year, benz acid is naturally stronger than your this type of dilute acid and decimal acid, that is of the order of 5m or 2m like that. So in that case, you have to put in the normal form. So concentrated acid to be expressed in normal form. As for example, concentrated sulfuric acid, that is of the order 36 normal. How strong you can imagine. Among all these acids, your concentrated sulfuric acid is very strong, that is 36 normal. And your hydrochloric acid is 12 normal or 11.5 normal. So, that is the sulfuric acid is a very strong acid. That is oil of vitriol, that is called oil of vitriol, very viscous acid, just like glycerin. Your sulfuric acid is very viscous due to intermolecular hydrogen bonding. Okay. So you see this, that means your normality of sodium hydroxide is equal to your 0.98 m/. So this is the normality calculated for what? Sodium hydroxide. So by this we can calculate the sodium hydroxide normality. Instead of rough calculation, like that's why putting 2 pellets, it will be like this, normality will be like that. If you add 3 pellets, it will be like this. This is a rough calculation. Whenever we make different types of sodium hydroxide solution for bench acid purposes or bench purposes, that we roughly add some pellets of sodium hydroxide to some volume of water, so that roughly we get the normality. But this is the exact way of calculate the normal strength or molar strength. This is also same as molar strength. Sodium hydroxide normality, molarity will be identical. So this is a normal solution, and also you can call it molar solution. So normality of sodium hydroxide you can calculate like this. Okay. So now we have prepared oxalic acid, and exactly we will prepare the decimal solution, and with reference to that oxalic acid, that is the weak acid, we are titrating against the unknown alkali of unknown strength that we can calculate. That is titrat. The normality, if you know it, that is called titrant. There are 2 things here using. Here one is using titrant and another we are using titrat. The process is called titration. Okay, thank you all.